Hello class, you are most welcome. Today we are going to look at the determinations of the focal length using a convex lens. And in that, there are parameters that we need to have. So the materials that we need to have when you want to determine the focal length of the convex lens. One, we need to have a lens, and in this, the lens that we should have is supposed to be a convex lens, and this is what we call a convex lens. Then also we need to have a lens holders, which will help to put our lens, and this is the lens holder that we shall be able to use. Then also we need to have a spring with a gauge, and the gauge will act as our object that we shall be able to get its image. And this is the spring. You can see this is the gauge that we have. Then also we need to have the white screen, where this is the white screen where our image shall be located. Then also we need to have a touch bar with the holders, and this is the touch bar. This is our touch bar, and this is the holder. Then also we need to have a meter rule, and here it is the meter rule. It has those marking on them that we have to measure for us the distance. Then also we need to have a switch, and this is the switch that we shall be able to use in this particular experiment. Then lastly, we are supposed to have a fresh dry cells, and it should be a pair, and this is our fresh dry cells. Yes, let's look at the experimental setup of our experiment. Now, in the setup of the experiment, the lens together with the holder is placed between the screen with the gauge and the white screen, such that the touch bar is put behind the wire gauge to allow the light to pass through the wire gauge, and the image of the wire gauge is seen in the screen. Then this touch bar is put on the wooden block, such that it will help to raise the height of the touch bar to be in line with the wire gauge. Then this valve is connected to the switch and also connected to the dry cells. So this one is how our experiment will be. Then also we shall see that in the experiment, as we shall be performing, the distance that will be between our wire gauge, which is taken to be the object, and the lens, this distance we give it to be u, which is the object distance that we shall be able to have. Then the distance between the lens and the white screen, that distance is our image distance. Hello. Having already seen the experimental setup, let's now consider the setup and in our real world. Now in the setup, also our experiment, we shall put the order patterns. We are going to put them in a way that what our experiment is saying. Now if we are to see, this line is saying it is the meter rule. Let's start by putting our uniform meter rule, and here it is the meter rule. Let's put it like that. Then also, in this we have a screen with a gauge. Let's come and put it this side. This is our screen with a gauge. Then behind the screen with the gauge we have the wooden block. I think this is our wooden block. Let's put it behind. Then on top of the wooden block we have the touch valve, which is here. Let's put the touch valve. Then here we have already connected. This is where our dry cell is. It's already been put there, and this is the switch. Then in between the wire gauge and the screen we have the lens with the holder. This is there. It is here now. We have already put it. Then this is also our white screen that we also have it there. Now, having already set your experiment like that, now what demands is that we are going to set the distance to be in a way that it is greater than the focal length of our lens. Why do we have to do that? If the object is put in the focal length, then the nature of the image is always formed at infinity. It means that at that moment, even if you adjust the distance of the screen, you cannot be able to get the object distance. So it means that we need to put our object U to be greater than the focal length of our lens here. So
Thank you. We have said earlier that when the object is placed at the principal focus, the image of that object is always formed at infinity. So if you are to consider these simulations, we shall see that this line is what we call the principal axis. Then ray or the arrow here, we are taking to be the object. And this one is the principal focus of our lens. And this lens is the convex lens. Then if we are to reduce on the focal length of the lens, we can see that may reduce a bit and also reduce on the diameter of the lens. Now, if the object is placed at the principal focus or the focal length of the lens, what shall be the nature of this image? So let's bring the principal rays and see the nature of this image. Now we are seeing that if the object is at the focal length or the principal focus, the rays does not meet. So the rays just continue. This tells us that the image of this object is formed at infinity. Therefore, it is advisable, if you are going to put the object distance, you should make sure that the object distance is greater than this focal length, so that the image is always formed in the screen. So if we are to consider this, and we bring the ruler and measure this focal length, we shall see that if this is the focal length of our lens, then the object distance should be greater than this focal length, so that the image is always formed on the screen. So let's see if we are to increase the object distance. So if we have increased the object distance, then this ray can meet. So it means that the moment the object is put behind the principal focus or the focal length of the lens, then the image is always formed on the screen.
So now let's put, since the focal length of the lens we have already determined on the quadrant is 10, we are going to put the distance U to be greater than 10. So we can start from 15, 20, 25, and the rest of it. So let's start arranging. We put this lens together with the holder to be at a distance greater than the focal length, and of this case, we are taking to be at 15 centimeters. Now when you put the gauge and the lens at a distance of 15 centimeters, which is already greater than the focal length, and this one now becomes our distance U, then we are going to lit, or we shall light the bulb, so that the light from the bulb moves to the screen. So let's light the bulb and we see. So if I'm to close the switch, then we shall be able to see the light there. And this is the light that we have. See, it is now dimmed. So that is our bulb that we have there. So now seeing the bulb is giving light, let's put so that we are able to see it. Now, having already put and set up your object, you already put our object U to be at a distance of 15 centimeters. Now we are going to move the screen to and fro until a clear sharp image of this wire gauge is seen in the screen. So we are seeing now it here, but let's move to and fro until a clear sharp image is formed. I think this one we are seeing it is blurred. Let's continue taking it backward until a clear sharp image is formed. I think there is an image there that we are seeing. That is now sharp. Let's move to and fro. I think that is the distance. So now we are able to see the wire gauge there. Now, if now we are able now to see the wire gauge clearly, then we shall be able to get the distance V. And how do we get this distance V? We have already done that. We have already put our object distance U is equals to 15.0 centimeters. Now, if we want to get the distance V, we read the positions of the screens. And here in that, the position of the screen, we are seeing it is at 47.8. So now, seeing the screen that it is at 47.8. So we shall have now the 47.8 minus where the length is. And seeing the length is at 15, then we shall have it minus 15 centimeters. The whole thing is under centimeters. So now if you want to get the distance V, therefore the distance V now becomes the 47.8 minus 15 centimeters. Now when we do that, then we shall be able to see that our length, it is at the distance of 32.8 centimeters. So that one becomes the object distance. So if the object is at 15 centimeters, the image is formed at the distance of 32.8 centimeters. Now I have already got the distance U and also got the distance of V. The next thing is that you will keep on repeating the experiment. Keep on repeating the experiment by changing the distance U. So here we are going to keep on repeating the experiment by changing the distance U. Seeing you're starting with 15.0, then we can adjust the distance or we increase the distance to 20.0. So now when we increase the distance of U to 20.0, still you do the same thing. You adjust this one to and fro until a clear sharp image is formed. Now as you can see, this is a clear sharp image. So now when we have already seen the screen, the image of the cross wire, still you do the same thing, you get the distance between the lens and the screen. So the distance between the lens and the screen also gives you the object distance. Now when you keep on repeating the experiment by changing the distance U to 20.0, 25.0, 30.0 and the rest of it.
We have already seen how the object should be put for us to locate the image. So now let's change this object to the light. So now this one is our object. This is the optical axis. This is the principal focus. This is our convex lens. And this is the screen. So if we are to level, this is the screen. This is the convex lens. This is the principal focus. This is the object. And this is the optical axis. Now, we have already said that if we put the object, and in this case our object is now the light, we put it at the principal focus. Here, the image is going to be formed at infinity, meaning that the image shall not be formed on the screen. So let's reduce on the size of our object. Then let's bring in the light and we see. So let me remove the principal ray. Then if we are to see here, even if we adjust the screen, the sharp pale of light will not be formed. And since the sharp pale of light cannot be formed, telling us that the image here is formed at infinity, which means even if we keep on adjusting, we shall not be able to see the image. Then, if we are now to put the object beyond the principal focus or the focal length, when I adjust this beyond the optical lens, then we are seeing that this focal length is at 120. Then, if we are to adjust this screen to and fro, so at the point where we are going to have a sharp field of light they are meeting. Think that is, if we are to bring in the ray, we cannot even see the imaginary ray if they meet at that point. Then it means that the distance between our bulb and the lens, this distance is the object distance. Now that we have already measured the object distance and it is 120, then the distance between the lens and the screen is the image distance. So we can also measure that image distance. Then you can see that the image distance here is at 240. 240. Now you just keep on doing the same thing. You increased the object distance, like if we were to increase our object distance to 160, we increase the object distance to 160. Then you removed the meter rule and also adjust this one to and fro until a clear sharp image is formed. Then if you get the clear sharp image form, you measure this distance V. So now you keep on repeating the experiment by varying the distance U. As you increase the distance U, we shall see that the distance V will keep on decreasing. So here you just keep on repeating the experiment for different values of U to get the different values of the V.
And the rest of it. Then now you are going to tabulate your results in a suitable table. Then that result, you will be able to plot it in your graph. Yes. Having already performed the experiments, and we started with the U equals to 15.0, we come to 20.0, come to 25.0, and we have 30.0, up 25.0. Then in the table of values, we are going to include the column for UV, which is in centimeters squared, and also we shall include the column for U plus V in centimeters. And this one now becomes the calculated values that we will use your calculator to simplify them. And then as you can see, our initials U, when we have done it there, it was started to 0.8. Now, for you now to come up with UV, it's just the multiplications between U and V. So for this row, it is 15.0 times 30.8, you enter the value here. Then for U plus V, it is 15.0 plus 32.8. You come and also enter the value here. So that's what we will do now. Let's look at now the table of values. Having already performed the experiment by varying the distance U and also calculated the distance V. When U is 15, we found V is 32.8. When U is 20, we found V is 21.5. When V is 25.0, we found when U is 25.0, we found V is 18.3, etc. When the experiment has been repeated for different values of U, and here we see that U is 15.0, 20.0, 25.0, 30.0, and 35.0, we got our V. So it means that in our table of values, we include the value of UV and also we include the value of U plus V. Or which, if we want to get the value of UV, we multiply it with 15.0 times 30.8, we get that. Then when we want to get the value of U plus V, we add 15.0 plus 32.8. Then we are able to get 47.8 and set. Now, when this table has already been filled out, the next thing is that we need to plot a graph. And the graph that we are going to plot, we shall plot the graph of U plus V against UV, if we want to get this dot. Then now when the graph has been plotted, and we have a graph of U plus V against UV, we shall be able to have such a graph. Vertically we plot U plus V, and horizontally we plot UV. Therefore, the the slope of such graphs if you have already plotted it. And here in the slope you have the change in u plus v against the change uv. And the slope of such graphs S, these slopes of the graph S is the same as the focal length of the lens. The slope of such a graph will be equal to the focal length of the lens. But now, to Sabine, at a later time, it's unknown how can we plot such a graph and how can we read such a graph in the slope. But particularly, when you get the slope of such a graph, u plus v against uv, then that slope is the same as